The name of this video is External Dirichlet problem. As it turns out, the more proper pronunciation of this name is Dirichlet, not Dirichlet. Consider we have a block of copper, for example, that is a conducting material in macroscopic electrostatic equilibrium under the usual normal conditions we already discussed in previous videos. So let us suppose that this object resides in my lab, which for us now is the entire universe. So the entire universe is this box here. This box occupies a region which we call capital gamma. Within this region, we have our conducting object. There is vacuum elsewhere. The region within the object, that is in the bulk, we call it capital omega minus, whereas the negative space on the other side, which is capital omega plus, is the vacuum outside. The summation of these two, in addition to the surface capital sigma of the conducting object, gives us the entire universe. So the entire universe, which is the lab, if you want, in this case, is comprised of capital omega minus union capital sigma union capital omega plus. This is our entire space. And let us suppose that we inject a charge, a small q, on this object, that is, the object is originally charged, and we inject it in such a way that there will be, at each point, capital Q on this object, a sigma of capital Q, which is our local surface charge density at each point capital Q. In macroscopic electrostatic equilibrium, we know that no matter what, the electrostatic field within the object has to be equal to 0. So there is no ρ within the object. So in principle, we need only to consider capital sigma, no more than that, when we are considering the conducting object. How do we solve problems in this case? Of course, we can solve it using Coulomb's line superposition principle or any other equation which involves the electrostatic field E. However, we want to solve it using only a scalar function V at any point, which now on, instead of calling capital P, let's call it more mathematically vector R, which, if I choose any origin of vector somewhere here in space, a point here could be a vector R in general, and this point can be anywhere you want. We are exploring the entire space, inside and outside the conducting object, everywhere in the lab, that is, using a scalar function. There are 5 steps that you need to use in order to solve such a problem. Step number 1, the electrostatic potential is always a continuous function. Let's write those in red here. Point 1, V of R has to be a continuous function, C naught, everywhere in capital omega, in the entire lab or universe. Step number 2, and in fact step number 2 is the one you typically use in the beginning of any problem solving scenario, normal conditions at infinity. Since the object is finite, is limited in space, the limit for R that goes to plus infinite of V of R has to be equal to 0. You usually use this, and then you verify the end continuity. That's the first step to do. The next step is actually to notice that in the vacuum region capital omega plus, we have no charges. So what equation is fulfilled in that region? Laplace equation. So the scalar Laplacian of V of R has to be equal to 0. Okay, so as I said, first you want to do this limit, but actually the very first step is really that you want to set up your Laplace equation. Okay, so this I'm going with a sort of pedagogical approach outlining them. I will re-put numbers here for when we solve actually a problem, okay? I'm sorry not to confuse you. I really want to be sure that this is a pedagogical approach, and now here we will put numbers as to use in a problem. In fact, this is the origin of everything. Then we use the limit, okay? Okay, the fourth condition we want to use, the fourth step, is Coulomb's theorem in integral form for V, which tells us that minus the integral on the limiting surface capital sigma plus from outside of the normal derivative. In examples, we'll clarify this concept, because of course you want to write this with respect to a coordinate system of V of R, dA, has to be equal to 1 over epsilon naught, the surface integral on the entire surface closed capital sigma of sigma at point Q dA, which means on any point on the surface capital sigma of the conducting object. Lastly, we must impose that the electrostatic potential V at any point R, which is part of the union between the surface capital sigma and the bulk of the conducting object, has to be constant. Okay, on the surface, we know that it has to be constant. As we have seen in a previous video, there was a discussion that you were supposed to do in Piazza. Since the tangent components of the electrostatic field are 0 on the conductor, there is no need to perform any work to move a charge on the surface capital sigma. That is an equipotential surface. So obviously, equipotential means that potential is constant on the surface. And as it turns out, since it has to be a continuous function, it has to be constant all the way to the inner region of the object as well, where the electrostatic field in fact is 0. So the fact that E is equal to minus gradient of V and V is constant inside makes sense. V is constant, the gradient is 0, which means anywhere on the surface, on the boundary included, and everywhere in the bulk, the potential has to be constant. So in problems, the way you actually proceed is, 1, you set up your PDE, partial differential equation, which in our case is going to be simplified. I will tell you this in a minute, which is Laplace equation. Then you impose normal conditions and infinite. Of course, here it's a second order differential equation, so this leads to usually two unknowns, alpha and beta. Typically, this condition allows you to find one of the two, let's say beta. So you solve one of the two and one is still left. The next step to find the other unknown is to use Coulomb's theorem down here. So this is step 3. This allows us to find the other unknown alpha of the two unknowns. Then we impose 4 that we check, we verify that the potential is constant on capital sigma n within the object. And finally, we verify the continuity of the electrostatic potential, which is always true. Now, in this course, we are going to solve only very simple partial differential equations. So what type of equations are we going to solve in this course? For 3 symmetric situations, okay? So we're going to solve it for a sphere with a certain radius. We will give an example soon about that. So in this case, if this is a spherical coordinate system, I only sketch OR. The solution for this specific case of Laplace equation, when there is a spherical symmetry, is very simple. It tells us that V of R is equal alpha divided by R plus beta. I will give an example soon. Another scenario is an infinite plane, an infinite conducting plane. Again, it goes to infinite. In this case, because of the symmetries of this problem, we are only interested in the z-axis, the origin here. So in this specific case, the potential is going to be alpha z plus beta. And lastly, the very last scenario I'm going to sketch here is that of a cylinder, an infinite cylinder. So this extends to infinite. In this specific case, we have R, this is the origin. The solution is the most complicated one, is alpha natural logarithm of r divided by beta. Okay. So note that I wrote it in this way. Of course, you could write it natural logarithm of r minus natural logarithm of beta, which is an additive constant. I put it like this because the argument of a logarithm cannot be with dimensions neither. So this beta has to have dimension meters in order to make it dimensionless. So these are the only three scenarios we are going to encounter. In fact, by means of these three scenarios, we can solve lots of interesting problems. For example, the problem of a spherical capacitor, the problem of a parallel plate capacitor, the problem of a cylindrical capacitor. If you remember the homemade AM radio, which I've shown you at the beginning of this course, actually the aluminum foil capacitor used in that radio is a cylindrical type of capacitor. And if in fact you use the dimensions, we'll come back to this later, for that I use in the radio, you actually really get the proper result for the capacitance. So it's really important to solve this kind of problems. Of course, later on, if you study a book like Jackson, you're going to solve much more complicated PDEs, which are not symmetric cases, but completely arbitrary with all these conditions. And these allow you, in principle, to solve any electrostatic potential for any conducting object. So in summary, this is called the external Dirichlet problem. 5 steps in this order. We're only going to consider 3 special cases. And now we're going to see an example. That's it.